superposition states, entanglement, spooky action at a distance and tunneling through insulating walls. Being somewhat counterintuitive, they are no doubt extremely useful constructs in theoretical and experimental physics. More uncertain, however, is whether or not these concepts are fundamental to biology and living processes. Of course, at the fundamental level all things are quantum, because all things are built from the quantized states and rules that govern atoms. But the real question is, when does the quantum mechanical toolkit become the best tool for the job? Enzymatic processes are catalytic mechanisms in the body for essential biochemical processes, for example hydrolysis of the neurotransmitter acetylcholine by the enzyme acetylolinestase. The paradigm for enzymatic reactions is the lock and key concept derived from the fact that the enzyme substrate binds into an active site on the enzyme structure, making particular intermolecular contacts with amino acid residues on the enzyme. These residues typically act as nucleophiles or acid-base catalysts in the reaction, which occurs only if these point contacts are made. As a key substrate fitting into a lock enzyme, the process of obtaining this particular arrangement, like a lock and key or a hand-in-glove between the enzyme and substrate, may involve orbital steering and pushes the substrate towards a transition state TS along the reaction trajectory from the initial reactant to the final product. Key experiments in 1966 by default chance first showed that a tunneling effect was present in enzymes. Quantum tunneling or tunneling, see spelling differences, is the quantum mechanical phenomenon where a subatomic particle passes through a potential barrier. Quantum tunneling is not predicted by the laws of classical mechanics where surmounting a potential barrier requires enough potential energy. Although it is very well established that quantum mechanical tunneling plays an important role in enzymatic processes that sustain life, it is still the case that this information is not fully applied in the development of catalysts, for example, which scientists still fail to make as efficient as biocatalysis by enzymes. Partly, this may be because it is not fully clear exactly what role the protein environment takes. It is hoped, however, that the theory and some concepts mentioned here highlight promise and that the developments will continue.